So, good morning, everyone. Today you have the pleasure to receive Dr. David Alonso as the speaker of our webinar. Dr. David is a postdoctoral fellow at the University of Oxford, and his research focuses on studies of the large-scale structure of the universe. And currently, he is also a member of the LSST collaboration. And today, he is going to talk about galaxy clustering and weak lensing with LSST. So, David Alonso, thank you very much for accepting our invitation to give this webinar. It's really a pleasure to receive you here. So now, feel free to start your presentation, okay?
Thanks, Jason, and thank you very much for inviting me. It's a very interesting. It's the first time I do a webinar, so it's going to be interesting for me too. I just like to say that everyone should feel free to interrupt me at any point if you have any questions. So I hope this can be as useful for everyone as possible. So I'm currently actually not a postdoc at Oxford. I'm a fellow at the University of Cardiff for this year, and then I'll return to Oxford next year. So just that small qualification, but I'm still part of the LSST, which is the main thing that I wanted to talk about today. So this is more or less the outline of my talk. I'll start by describing the kind of science in terms of dark energy that we hope to do with the LSST, and I'm going to be quite LSS centric. So I'm gonna focus a lot on the kind of projects that I'm involved in and the kinds of probes that I'm involved in. So the LSST is broader than what I'm going to talk about. So I'll talk about the main dark energy probes of the LSST, the main challenges that the LSST will try to tackle, and then I will focus. I was asked to kind of focus on the kinds of open projects or kinds of opportunities for engagement with LSST that are open right now. So I'll talk about 5 different projects that I'm involved in within LSST, which could be interesting maybe for other people in Brazil. And then I'll just summarize everything at the end. Right, so the LSST is the Large Synoptic Survey Telescope. Just a brief introduction for those who don't know about the LSST. The LSST will be the world's largest imager in terms of the camera. It will produce a catalog of objects that will be both wide in terms of the area coverage, deep in terms of how deep in magnitude it will go, and fast in the sense of it being able to cover the whole sky very, very often. And it will collect a huge amount of data. And with the LSST, we hope to do all kinds of sciences, but in particular for dark energy, we hope to be able to study cosmology, and in particular dark energy, through 5 different probes. And these are the ones that the Dark Energy Science Collaboration is interested in, the DESC or DESC, which you'll see that acronym later on. The 5 probes are supernovae, clusters of galaxies, strong and weak lensing, and large-scale structure. And I'm going to focus on these last 2, weak lensing and large-scale structure, in the next few slides. So for those who are not familiar with large-scale structure, let me introduce it very briefly. So the idea is that the dark energy affects the expansion of the universe, and the expansion of the universe will also have an impact on the statistics of the cosmic density field. So if you think about the perturbations in the cosmic density field, the expansion of the universe will affect both the distribution of those structures on different scales and the growth of those structures across time. And the idea is then to study these density fluctuations, and in large-scale structure, we want to do that by tracing the fluctuations in the number density of galaxies, under the assumption that the number density of galaxies traces approximately the density fluctuations in the underlying matter field. And from experience and embodied simulations, we know that this is true to a good extent. We know that where there's more matter, there tends to be more galaxies in broad terms. So in general, we can think that there must be some relationship between the galaxy over density and the matter over density, and this relationship might be in general non-local, non-linear, and kind of stochastic to some extent. But we have good theoretical and empirical reasons to expect that at least on sufficiently large scales there should be a linear relation between both quantities, and that therefore we should be able to describe the density field of galaxies on large scales by one single extra parameter, which we call the galaxy bias, and there's and that's one of the most important aspects of large scale structure. And the reason for that is that in particular, what we want to measure is this thing that we call the matter power spectrum, which is basically the amplitude of the density fluctuations over different scales. So on the y-axis here, you have the amplitude of density fluctuations as a function of the Fourier scales. So small scales are actually on the right-hand side, and large scales are on the left-hand side. So because with large-scale structure, where we have to marginalize over this unknown extra parameter, which is the galaxy bias, that means that we're not able to measure the overall scale of the power spectrum, which means that we can't really track its evolution across time. So the overall amplitude of fluctuations, we don't really know it. And that means that we can't really constrain the growth of structure with large-scale structure on its own. However, because large-scale structure is tracing the perturbations in the matter density field at exactly the same redshifts as the galaxies that you're observing, we can trace the kind of scale dependence of the matter power spectrum. So if there's any features, for example, the BAO feature or anything like that, we will be able to track those down with large-scale structure. And then there's the problem, as I said, that on very small scales, we know that the linear bias relation is going to fail, and we have to either throw those scales away, or we have to come up with better parameterizations of the relationship between the matter fluctuations and the density fluctuations of galaxies. So those are the limitations and the opportunities of large-scale structure. But the most interesting thing about LSST and future surveys like it is that it will not just do large-scale structure, it will do large-scale structure in combination with other probes, in particular with weak gravitational lensing. So again, a very brief introduction, which maybe all of you know about. So in weak gravitational lensing, the idea is that the intervening, so you have a given source, in this case a galaxy, a source of light, and the light that is emitted by this galaxy gets distorted by the intervening dark matter through gravitational lensing, and that effectively is going to distort the shape of that galaxy, and it's going to correlate the shapes of adjacent galaxies due to because these galaxies are seeing the same foreground structures. The good thing about this is that this distortion in the paths of photons is, because of the equivalence principle, it is going to trace the full matter fluctuation. So it's not going to preferably trace galaxies other than any other type of matter. So that means that in weak lensing, we don't have any bias parameter that we have to marginalize over. The bad thing about weak lensing is that we for a given source or a given shell of sources, the lensing signal for that shell of sources is sensitive to the full density fluctuations along the line of sight. So to the projection of all the density fluctuations from the redshift of those sources down to redshift 0. So that means that there's a huge projection effect along the line of sight, which basically washes out all the structures in terms of, or it washes out the scale dependence of the matter power spectrum. But that means that then weak lensing and large-scale structure almost perfectly complement each other, in the sense that because we don't have a bias in weak lensing, we can actually constrain the overall scale of the matter fluctuations, and therefore we can track the growth of structure as a function of redshift, which we couldn't do with large-scale structure. we cannot look at particular features in the matter power spectrum because they are washed out by the huge radial kernel of weak lensing. But we can do that with large scale structure, as I said. And then on small scales, weak lensing should have better chances of being able to obtain constraints because there's no bias, galaxy bias that it has to take care of. There will be other systematics on small scales, but at least they will be not as severe as the galaxy bias. So the combination of these two probes is very promising, and there's many indications that by combining them we can obtain really good constraints on dark energy parameters. And I just put here an example from a paper from a couple of years ago, where we forecasted the achievable constraints on two parameters that basically parameterize deviations from general relativity in this Horndeski family of models. So which you don't need to know about. It's just look at the ellipses and see how by combining large scale structure and weak lensing you can do much better than with each of them individually. Right. So LSST is going to be able to do great science for cosmology. However, and the reason for this is this combination of different probes, but also the fact that LSST will observe a huge amount of data. And if you have a huge amount of data, that means that you're going to have really good statistical errors, really small statistical errors, which in the case of LSST means that it's eventually going to become limited by systematic errors. And there's a number of systematic uncertainties that is going to have to face. And I've classified them in kind of three different classes. So first you have what I'm calling observational systematics. So anything that has to do with the practical ways in which you observe your galaxies. So first you have sky systematics, the fact that you're observing these galaxies through layers of different sky kind of contaminants. So one of them, for example, is galactic dust, which is going to affect the magnitudes of your galaxies, and therefore is going to propagate into depth fluctuations or photometric redshift fluctuations or whatever. You have star contamination in two different kinds. So by contaminating your galaxy sample and also by obscurating the galaxies that lie close to these stars. And then you have a large number of observational systematics associated with the observing conditions. For example, the air mass when a given image was taken, the seeing at the time of taking that image, the depth variations across the full survey footprint, etc. And this image here shows an example of how different types of systematic. In this case, this is the seeing and the exposure time, how they correlate with the observed mean number of galaxies that you would see, or the mean density of galaxies. And this is an example from a DESC paper. So basically, any of these systematics will affect will generate fluctuations in the number of galaxies that are not cosmological but purely systematic, and you have to be able to characterize them and subtract them or marginalize over them. And I'll get back to this in a second. Those are sky, what I'm calling sky systematics. There's also photometric redshifts. So I guess everyone's familiar with what photometric redshifts are. The idea is that we're not going to have a spectrograph in LSST. We're going to be able to measure the SED of galaxies in 5 different bands. And we have to infer a redshift from those 5 bands, and that means that we're going to have inaccurate redshift estimates. That in the best case scenario, that implies losing the small radial scales. But not only that, but because these redshift uncertainties are quite complicated, trying to do a 3D analysis like you would do in a spectroscopic survey is quite complicated. So you have to do something called tomography, where you bin your galaxies into bins of photometric redshift, and then try to characterize the redshift distribution of each of those redshift bins. And then use the cross correlations between all of those bins to obtain cosmology. And then the problem is trying to characterize the redshift distribution of those different tomographic bins, and there's different ways of doing that, and to some extent, all of those will give you different answers, and you have to marginalize over your uncertainty in that estimation. So you have, for example, these two kinds of observational systematics, and some of these systematics will actually correlate different classes of systematics. So dust, for example, will affect not just the depth variation, so it will affect not just the number of galaxies that you observe per unit area, but it will also affect the photometric redshifts of those galaxies. So you will have a coupling between the photometric redshifts and the density fluctuations. We have blending issues, which there will be a lot of for LSST. Blending will affect also photometric redshift. So if you have a blob of galaxies and you don't know what photon is coming from which galaxy, you're going to try to obtain photometric redshift for a blob of galaxies, and you're going to get some ridiculous answer that you have to interpret one way or another. Right, so that's for observational systematics. I don't know if there are any questions. Just feel free to stop me. Right, so that's observational systematics. The next class that I've defined here would be astrophysical systematics. So basically, any systematics that have to do with our lack of knowledge or our lack of understanding of how the fundamental quantities that we want to constrain, which are the density fluctuations of the universe, of the cosmic density field, how those are related to the things that we actually observe, which are complex astrophysical objects, which are galaxies. So in the case of galaxy clustering or large-scale structure, as I said, the main source of systematic uncertainty there is the actual galaxy bias, or the relationship between the overdensity of galaxies and the overdensity of matter. And you have to, beyond the linear level, you have to come up with different perturbative or empirical or effective theories that allow you to relate one quantity with the other. And the level of which the level to which your model actually corresponds to the data is a source of systematic uncertainty. Another source of systematic uncertainty that people don't talk so much about, but which could be quite relevant for LSST is magnification bias. So weak lensing will not only change the shapes of galaxies, but it will also alter the magnitudes of those galaxies and the number density, the apparent number density of those galaxies. So you have so lensing causes an extra perturbation in the density of galaxies that you're observing in large scale structure. And even though this is subdominant with respect to the main term, which is just the density of galaxies themselves, if you don't account for this term, or if you don't measure the amplitude of this term sufficiently with sufficient accuracy, you will end up biasing your final cosmological parameters, and this is something that we quantified in this other paper not so long ago. Right, so but that's for galaxy clustering, which is yeah.
May I ask a question? What is the BS, Carl?
What is what?
BS.
BS here, this is what we call the tidal bias. So the idea here is, so there are different ways of trying to understand the biasing relationship. This is one particular model, which is what I guess people just call it perturbation theory. So the idea is that you have some kind of perturbative expansion of the density field as a function of any scalars that you can form at first order, second order, etc. So at first order, the only scalar that you can form is just the density field itself. At second order, you have the density field squared, but you also have the tidal tensor. So these are the second derivatives of the Newtonian potential, and you can basically square that and take the trace of that tensor, and that gives you this term here. So in principle, you could have a bias. Yeah.
Thanks.
Yeah. And since you ask, this kind of perturbative expansion also applies to something else that I'm going to talk about in a second, which is intrinsic alignments, and people are hoping that this kind of treatment will also help characterize this intrinsic alignment. So let's actually move into that. So galaxy clustering is clearly hampered by these kinds of systematics, but there's also astrophysical systematics associated with weak lensing. I'm going to first talk about intrinsic alignment, since that's the one that I just mentioned. And the idea here is that in an ideal world, any correlated shapes between galaxies, the correlation of those shapes of galaxies would be just induced by the lensing effect, by the weak lensing effect. But it might be that even without that lensing, the shapes of galaxies, of nearby galaxies, would also be correlated with one another. And that makes sense to think that will happen. And one of the reasons is, for example, imagine that these two galaxies live close to the same cluster of galaxies, or live close to some over density, then one could imagine that that if these galaxies are have come from a merger of different objects, then the shapes of these galaxies will be oriented towards this larger mass or something like that. So there will be there are bound to be correlations between galaxies, between the shapes of nearby galaxies, and this is what we call intrinsic alignments. And you have to characterize them again and subtract them. Yeah, and I can talk more about this if people have questions later. So that's one source of uncertainty for weak lensing. The other one is what we call baryonic effects, and this is just the fact that if we want to measure the nonlinear matter power spectrum, we need to, in a perfect world, the only thing that we would have to do is run a number of relatively cheap embodied simulations containing only dark matter. And then from those embodied simulations, we will get an estimate of what the matter power spectrum is. However, if these simulations don't contain baryons, other matter components that are not that interact basically, which have viscosity and gas properties, then those simulations will not contain the whole story. So the whole picture. So you actually need to include baryonic physics in order to have a correct measurement of the matter power spectrum, and those are actually quite difficult to put into simulations in a correct way. And the idea is that you don't know about the kinds of processes that are happening below the resolution of your simulation, and it's very difficult to resolve very small things. So you have to put in by hand some of these effects. With parameters that you have to tune to observations. And there's different ways of doing that and different prescriptions, and all of those different prescriptions will give you a different prediction for the matter power spectrum. And these are just this is just a plot from Elisa Cesari's recent paper where they showed the variety of different predictions that you can get depending on which hydrodynamical embodied simulation you look at. So there are uncertainties to the level of at least 20%, 10 to 20% on the small scale power spectrum due to these baryonic effects, which we will need to account for. Okay, and finally, even if we have a perfect theory, and even if we've managed to get rid of all our observational systematic, we have the problem that maybe we are not understanding the statistics of our observables, and this is what I'm calling likelihood systematics. So we could begin by assuming that whatever observable we end up measuring, for example, some correlation functions or something like that, we can start by assuming that those observables will be Gaussianly distributed, in which case we just have to characterize the covariance of all of those observables, and that's actually quite challenging. We expect to measure maybe a data vector with LSST that will have very probably thousands of elements. The covariance matrix will therefore have of the order of 1 million elements, and if you want to compute that covariance matrix either by jackknives or embodied simulations, it's a nightmare. So you need to come up with other ways of measuring those or characterizing that covariance matrix, and there are many different open research projects in this direction. Then you have to also make sure that any parameters that you're trying to marginalize over, that you're propagating the correlation between that this parameter may have between different observables correctly. And one example of that, for example, is photometric redshift uncertainties. So those will affect both the weak lensing correlation functions and the galaxy clustering correlation functions and any cross correlations. And you need to be able to characterize the possible correlations induced by this common systematic. Even if we manage to compute a completely correct covariance matrix, there's the problem that maybe a covariance matrix will not be enough to actually characterize the statistics of our data, because the data may not be Gaussian. In which case we would need to look at higher order moments of the data, and there are indications that this might be the case, and the question of whether or not this will matter for LSST is still an open question that we need to assess. Right. So I'm going to move on to the projects that I'm involved in LSST. So I'd like to pause for a few seconds in case anyone has any questions about what I just talked about. If not, I'm gonna carry on and feel free to interrupt me if there's anything that you'd like me to repeat. Right. So I'm going to talk about the dark energy science collaboration, which as I said, I'm going to be calling DESC. First of all, before I go into the details of the different projects, I'll tell you a little bit about how we expect the LSST to be structured or rather DESC to be structured. So the LSST will take, so this is kind of one of these things that I really hate, which are these workflow kind of diagrams, which takes forever to understand, although I think this is simple enough that we can follow it. So LSST will take some raw data in the form of images with all kinds of contaminants. These raw data will be processed by the data management group, so which I'm going to call DM. And they will give us a number of processed data sets in the form, for example, of object catalogs, maps of different quantities, or maybe some processed or non-processed images. So all of these different types of processed data sets will be then transferred to the different science working groups. So these are the working groups that take care of producing the observables associated with each of the different cosmological probes.
So Dave, just a quick question. I mean, this will be produced at the NCSA, right? The map.
Say again?
The maps will be produced as part of the data reduction, is it?
Yes.
By NCSA.
Did you say NCSA?
Yeah.
I guess so. Yeah, I'm actually not sure of those, but yeah, that must be true. Yeah.
It's not a NERSC. I mean, it would be an NCSA data reduction. Okay. So.
Yeah, probably. So in DESC, we have these science working groups that take care of each of the different observables. So you have one for each of the 5 cosmological observables: large scale structure, weak lensing, clusters, supernovae, and strong lensing. And then you have an extra science working group, which is not associated to one particular cosmological observable, but which affects all of them, which is, as I said, the photometric redshifts. So there's a whole group in charge of dealing with photometric redshifts. So that all the different groups need input from the photometric redshift working group, and the idea is that through that interaction, there will these working groups will produce some kind of cosmological summary statistic. And one example of a summary statistic, to avoid using jargon too much, would be, for example, the correlation function of galaxies. So that's what LSST will produce. Sorry, what large scale structure will produce. And there may be joint data vectors, for example, the cross correlations between different probes and things like that. So once you have a data vector, then there's another analysis group called TJP, the Theory and Joint Probes working group, that takes care of producing the sufficient support for the comparison of that data vector with different theories and the generation of posterior distributions for different cosmological parameters. For example, the dark energy equation of states based on that theory and the summary statistics. So this is kind of what the analysis pipeline of LSST will kind of look like on super broad terms. And the 5 projects that I'm going to talk about are associated to different parts of this process. So I'm going to hopefully talk about these 5. I'll focus on 3 of them because they're in a slightly more advanced stage. And then in particular, I will focus in all of them at the end on what open projects and open avenues there are that maybe people would be interested in collaborating on. So I'm going to start with this thing called the Core Cosmology Library, which maybe some of you have heard about. And it's one of my favorite projects in LSST because it's working quite well, and I think it's going to be very useful. So the idea, the concept for the Core Cosmology Library, and this is taken directly from the README of the Core Cosmology Library, is to have a library that will provide routines to compute general cosmological observables with a validated numerical accuracy. And the idea here is that we're going to, with LSST, we hope to be able to do precision cosmology. So we need to be able to assess to what extent our theoretical predictions are accurate to the level that we need. So to the level at least that our statistical errors will require. So that means that we need a cosmology theory library that is validated to that precision, and that means cross-code comparisons. That means having a sufficiently good validation machinery in place. We're also going to have 5 different probes, and maybe even more when we cross-correlate with other data sets. A number of different probes generating data vectors, and then using those data vectors to get cosmological parameters. That means that the different likelihood modules that each of those probes will use, and any joint likelihood modules, will need to be consistent. We can't have one of the for example, clusters using one prescription of the mass function that is completely different from whatever a large-scale structure is using for their HOD modes or anything like that. So we need to have a framework that allows you to check for consistency and avoid inconsistencies, or at least warn about those inconsistencies. And also, we hope for that this core cosmology library will be useful not just for LSST, but for any cosmologist. So we in LSST in particular, we will be interested in cross-correlating our data with, for example, CMB or anything else. So we want the library to be general enough that it's useful for anyone doing cosmology, basically. So I've put a link there, and I'll get back to that link later. This is kind of the current science capabilities of the core cosmology library, CCL. So basically, a user would create a cosmology object based on a number of cosmological parameters. That cosmology object then can be used to compute a matter power spectrum using a wide variety of different methods. And from that cosmology and its associated matter power spectrum, you can compute a number of different observables. So background, distances, growths, etc. as a function of redshift. You can characterize different, what I'm calling here tracers, which are basically different, effectively different tracers of the matter distribution, galaxy clustering, weak lensing, CMB lensing, and many others that you could think of. And this should contain information about their associated astrophysical systematics, and also things like the halo model quantities that many of these different probes will need. Then a combination of these kind of primary observables will be used to generate these secondary observables, things like angular power spectra, angular correlation functions, and things like that, which will be the direct observables that LSST will produce. So that's in terms of the science capabilities right now, and I can tell you more about what LSST can, what CCL can do right now. But in terms of software, currently the code is maintained as a GitHub repository, which is completely open, and people can clone it and use it. It's public. The inside of CCL is C code, so that the library is quite it performs quite well numerically and computationally, and we provide a Python wrapper so that you could call it from Python. And the idea is that all the hardcore calculations are done at the C level, and then users will use Python to call all the different functions from it. And just to give you an example of how easy it is to use, this is just the 6 lines that you would need in order to produce a CMB lensing power spectrum for a given cosmological model. So we've been developing CCL for about a year now, and there will be a paper coming out soon, hopefully. And this has been a very nice experience, a very educational experience. We have right now 31 contributors. That means 31 cosmologists that have contributed code actually to the library. And I think the state at which the library is right now is quite. It's beginning to be extremely useful, and people are starting to use it for their own projects, and it's being used in actual science papers. But it's been a really interesting experience to actually develop code with 31 cosmologists. So I'd just like to mention a few of the things that we've learned through that. So this is just a picture from actually the first hack week that we had. So LSST or rather DESC hosts these meetings called Hack Weeks, where basically a bunch of people sit together and just code and work on particular projects. And there's basically zero talks. It's just work, and those are quite useful. And we managed to give the CCL a huge push in this first Hack Week. So this is just a few of the people that were there at that Hack Week, but there's, as I said, 23 other people that you cannot see here. So some of the things that we've learned through this is that basically, if you're developing code with other people, even if the number of those other people is 2, it's very useful to use GitHub or any repository-based platform like that. It's very useful to use pull requests to update the contributions of different developers, and also having a very strict code review. So if you have 31 people trying to modify the code at the same time, you need to make sure that anything that goes into the final mastered branch of the code is completely correct. And so you need to be quite strict in how you review that code and actually accept new modifications to the code. Any new science that we put into CCL is subject to external benchmarks. That means if I want to, for example, implement a new nonlinear biasing model or anything like that, it's not enough for me to implement that in CCL. Someone else needs to implement their own code, and we need to compare those two predictions and make sure that they agree to at least a sufficiently well-documented accuracy. It's very important to have unit tests. That means for any of these new science things that you implement, you should create a benchmark and a unit test such that whenever you want, you can run all of those unit tests and make sure that any new modifications to the library that you've made don't screw up any of those tests. And this is extremely useful, so that's why it appears twice in this list. We have lots of telecons to talk about code development, which can be very boring and very interesting at the same time. It's quite surprising. And it's having a good project manager, so someone that actually rallies the troops and brings everyone together and keeps track of the different changes is quite important. And that in this case, this has been Elisa Chisari. And as I said, hopefully there will be a paper documenting the library out very soon. But in the meantime, I encourage everyone to start using it.
Dave, do you use any specific tool for this project management? Or?
Say again? Not really. It's through GitHub. There's a few additional add-ons that you can use on your GitHub repository that allow you to, for example, see whether or not any modifications that you make are sufficiently well documented or sufficiently well unit tested and things like that. And we use those to kind of keep track of the changes and to make sure that the library is in a good shape. I think Elisa's the main thing that Elisa has done, and she has done it really, really well, is just not being discouraged by the maybe periods of time where people are very busy and no one's contributing, but still we need to talk, we need to meet, we need to make sure that everyone, that the different issues that the library has are being solved, blah, blah, blah. So it's just being on top of the project. I wouldn't say there have been any technical aids there other than Elisa being quite good at it.
Let me ask another question. I see everybody smiling. Do they smile all the time, or their attentions?
No, actually, I think we've been quite good at this. Even, I think, so there's two things that you have to be, I think, when it's 31 people coding up, is you have to have small egos, and be open to criticism. And I think everyone, at least who has contributed to this, has been quite good at this. So if you make some code, there's going to be bugs, and we have to understand that everyone makes bugs, and that none of us are the most expert coders. So when anyone gives you any criticism, you have to take it and discuss it openly and without getting angry. And that, I think, so far it's worked quite well. But it's true that that can be tricky, but it's been working well. Yeah.
Thank you.
Right. So it may be more interesting for everyone else is what kind of open projects there are in CCL. So CCL is doing a lot of stuff now, but not everything. One of the most urgent things that we need, and it's something that we're going to start working on now, meaning after I'm done with this telecon, I'm going to start working on it, is is implementing more generic non-linearity models. For example, this perturbative approach that I was talking about at the beginning. And that will include also halo models, for example, for the matter power spectrum of different tracers. There's a new there's need to implement cosmologies beyond WCDM in the library, and some people are starting to think about that. Right now we have to support for 2-point functions, but hopefully at some point we will want to try to get cosmological parameters from higher order correlations, and there's none of that implemented yet. We need to be consistent when we add large-scale structure or weak lensing correlations with the CMB, and to some extent we are, but there are some of these like the ISW and some other correlations that are not completely consistent, so it'd be good to actually look at that. And other things like primordial non-Gaussianity are not there yet. So there's a list of things that need to be done, and you can actually find a list of them in this URL here that I pasted. So I'm realizing that I'm running out of time, but I'm glad that I managed to talk about CCL, which is my favorite project of all of these. So I'm going to move on quickly through the other ones. Maybe make some emphasis on the things that need to be done for all of them. But anyway, interrupt me if you have any questions anyway. Right. So the second project that I want to talk about is the large-scale structure loop, and the idea is as follows. The idea is to have a fast round trip that allows you to take some cosmological parameters, generate a realization of what LSST should observe given those cosmological parameters, put dirt in those data. So for example, put contamination from photoseeds or dust or stars or whatever, push it through our pipeline, and try to recover the same cosmological parameters that went in, or at least study to what extent the dirt that we put in prevent us from doing that. And there are different pieces that go through this, that allow you to go through the different steps in this loop. There's this tool called Colore that allows you to generate these very fast realizations of what LSST should observe. Fastcat, which is the tool that allows you to put dirt into those catalogs. Then there's NaMaster, which is our preferred 2-point function calculator right now. It's just something that allows you to compute power spectra, angular power spectra. Then through CCL and a likelihood module that we generated, we can then connect those power spectra, those 2-point functions, with cosmological parameters again. So the motivation for doing this in large-scale structure, which is the working group that I co-lead right now, is to, first of all, to make sure that we have all the necessary pieces or all the necessary software modules to actually analyze the data, to incrementally improve those pipeline elements by gradually adding more and more realism into the dirt that we put into the data. And not only that, not only for kind of infrastructure tasks, but we also hope that this round trip can be used for science. So there's many questions that we don't know the answer to that could be answered through this kind of infrastructure. So, and I'll give a couple of examples later. So as I said, there's these 5 different pieces of software that you need to go through the whole loop, and that basically make up the analysis pipeline for large-scale structure. And if you click on each of these names when you get the slides, they will actually take you to different GitHub repositories. So these are all active repositories. So the first one, I'm not going to dwell into this too much because it's not super interesting, but I just very quickly mentioned Colore and NaMaster, which are the 2 of the main pieces of software here. So Colore is just something that allows you to generate very quick embodied simulations and then populate those with different observables. And right now what we have is galaxy clustering, weak lensing, intensity mapping, CMB lensing, and also ISW. And also, actually, we have Lyman alpha as well. So it's basically a way of generating many probes of the same underlying matter fluctuations. So Colore generates those as you would measure them if you had a perfect machine. And then Fastcat, which is this other code, takes care of adding dirt, for example, photometric redshifts or depth variations. And as I will mention, there are some open issues in Fastcat that would need work to resolve. And then there's NaMaster, which is this code that given a map of the sky, meaning a map, for example, of the density field of galaxies, and also given a list of possible systematics that could be contaminating this map, it will compute the correlation or the power spectrum of that map, marginalizing automatically over all of those different systematics. So I think it's a very useful tool in that sense for the kinds of things that we want to do with LSST. So I'm not going to dwell into the detail more. There's another complicated flowchart that you don't need to understand. So the current status of the loop is that we've managed to make a full loop for ideal conditions, basically running an ideal simulation, passing it through our pipeline and recovering the same cosmological parameters. And I'm exemplifying it here through the power spectra that were generated and then predicted by our likelihood, and they agree quite well even on very small scales. So that's pretty good. And we actually managed to run the first chains during the Slack meeting in February. So that puts this project in a very interesting stage, which is you can start actually using it for science and start improving it. And that's what will talk about in 2 seconds here. So things that need to be done for this LSS loop is finishing the validation at the likelihood level. As I said, we ran a couple of chains, but we need to do that better. We need to implement more complex systematics in fastcat, for example, maybe more realistic dust maps or more realistic depth variation, things like that, and scale it up. So right now, Colore can generate really fast and huge simulations, but actually the bottleneck is fastcat reading in those simulations and doing stuff to them. So maybe being able to make fastcat faster would be pretty good. And then I think the most interesting thing is actually starting to use this code or this infrastructure for science. So to actually put out papers. And the idea is that there's many things that this could be used for. One would be trying to see to what extent the correlation that I mentioned at the beginning between dust, contamination, and photoseas would make your analysis more complicated. For example, to study the correlation between the clustering strength, so between the bias of your galaxies and the photosea properties of those galaxies, we expect that large red galaxies, which will have better photoseas, but they also have a stronger clustering bias. So if you combine those with other types of galaxies, will that give rise to weird behaviors on small scale, something like that? And one of the things that are quite interesting for LSST, and which I think is still an open research question, is we've been relying on dust maps coming from CMB experiments, and those have a limited resolution. Is that resolution good enough for us or not? And you could take realizations of maybe highly resolved dust maps, pass them through your pipeline, and see what kinds of dirt they induce in your power spectra, and see whether or not you can actually deal with that. So those are kind of open questions that are interesting. So in the last 3 minutes, I'm just going to go through a lot of slides, but I'm just going to focus on the most important parts of the other 3 projects. So there's another project we have been working on, which is trying to use the tools that we've developed in LSST to analyze the large-scale structure data in the hypersubprime CAM data release 1 data, so the HSC data set. And this is kind of a picture of what those data look like on the sky. The motivation for doing this is that HSC, the data coming out of HSC is using the same data reduction pipeline that LSST will use, which means that we can learn a lot from those data in terms of what the LSST will look like, and maybe try to improve that reduction pipeline so that we actually make sure that we have the right amount of information for LSST. And also, this is data that is not being used for galaxy clustering. This is being used mostly for weak lensing. So this is state-of-the-art data that is not being used for this. So we could take advantage of it and actually start doing some science with it. And one of the things that we want to do is actually prove that you can do a power spectrum-based, so a Fourier space based analysis pipeline with this kind of data, which is not only proving that you can do it, but also proving that things like what I mentioned before, being able to automatically marginalize over sky systematics, which is something that you can do with these power spectrum codes, is very beneficial and showing that that these kinds of approaches are the right way of doing things. Right, so we've been doing work on this. We've been characterizing different systematics maps. I don't know if there's a question.
Yeah,
no?
just what is the total area of the HSC?
The area right now is about 100 square degrees. It's not huge, but as a proof of concept, and there's a few science cases that this is enough for example, magnification. But as a proof of concept, it's interesting. Sorry.
Not for large scale, right? 100
no, exactly. No, not yet. Yeah. In terms of depth, for example, it's huge. So if there are some things that you could try to do, like magnification or just proving that you can do a CL analysis down to these depths is interesting.
Okay, thanks.
So we've been characterizing some of the different systematics, like depth variations, dust, stars, the mask itself. And we measured the power spectrum in all of these different patches of the sky and verified that through our code, we are able to recover basically compatible power spectra across all of the different patches, which means none of these systematics seem to be affecting our final measurements too much, which is good. And then in the last collaboration meeting, we actually made a breakthrough, started characterizing the photo-C redshift distributions, and got a theory prediction for this, which agrees quite well with the data. And this is using the simplest kind of bias model, which is just a linear bias model, and it agrees with the data quite well to really small scale. So we're quite happy. But there's still a lot of work that needs to be done here. Particularly in characterizing other possible systematics that will start affecting us as soon as we start cutting in photo-C. And then once this is done and we understand the photo-Cs better, then try to do the full cosmological analysis, maybe marginalize them over a couple of parameters. So there's, again, a GitHub repository for this project, and there's a lot of open issues there that anyone interested would be more than welcome to work on, and you can contact me or anyone else in the large-scale structure working group to do this. And the last two projects that I'm going to talk about have started very recently, so I don't have a lot to say about them. The first one is the 3x2 pipeline. So LSST is starting to work on the pipeline that will produce the science that will produce the science observable that we think will give us most of the information, or at least a lot of the information about dark energy, which is the combination of the autocorrelations of galaxy clustering, weak lensing, and their cross correlation. So it's what we call the 3x2 point. So there's many good reasons, as I said before, for doing this kind of joint analysis, and the idea is to develop this huge analysis pipeline that will take us from the full data management catalogs down to the summary statistic, in this case, different types of correlation functions. And this is being led by Jossons here in this picture. Lots of different things that need to be done, because this has only started recently, and I think some of you guys in Brazil are actually involved in some of these. I know Antonino is going to be involved, and lots of applications once it's done. So this is a very exciting project, which is just starting now. So if you're interested, just go to this GitHub issue and start talking to people. The other one that we started literally 3 weeks ago, I would say, is TJPCosmo, which would be the joint analysis, the joint likelihood pipeline for LSST. So the idea is that it will take the data from all the different probes, combine them, and give you cosmological parameters. So it's the main motivation for this is being able to do this in a robust way that allows you to account for correlations between different probes, to check for consistency between different probes, and also to have a formalism that is generic enough so that you can implement different types of systematic models that you can marginalize over easily. And I don't have time to say much more, other than the fact that we had our first hackathon in Oxford 3 weeks ago after the latest large-scale structure conference here. And out of it, we have a first working version of the 3 times 2 point likelihood, a very simplified version, which allows us to marginalize over cosmological parameters and some systematics like the galactic bias and the intrinsic alignment amplitude. And we managed to get posteriors that agreed well with the test data that we put in. Right, so this is it. I'll leave the summary here because I'm way over time. And I'll just take any questions if you guys have any. Thank you.
Okay, thank you, Dave, for your presentation. So we have time for a couple of questions. So do we have questions from the audience?
I just wanted to know, Dave, great talk, very useful. Tell me, are you going to be in the all hands meeting? Do you have plans for parallel sessions
in the next one in Pittsburgh?
Yeah, in August. No, I'm talking about August.
August. Is that an LSST consortium meeting or?
Yeah. Mm-hmm.
I won't be in that one. No, probably not, because I have to be in another conference for that. I'll be in the DESC collaboration meeting which is happening in Pittsburgh in July.
Okay.
Yeah.
Will there be any action there? I mean, even if you're not there, or?
In the thing is that if you're talking about the LSST corporation meeting or collaboration, I don't know what they're
about the August meeting in Tucson.
Yeah, that's the one usually. So that tends to be more general because it's not just about the dark energy probes. And to be honest, I've never been to one of those, but I think if in terms of work getting done, I would say you get more work done in the collaboration meetings. Yeah.
I understand. Okay.
Do we have any other questions? So if we don't have any other questions, I'd like to say thank you, Dave, for your presentation. Thank you very much for coming. And everybody, let's thank Dave for his presentation. So
thank you.
Thank you, Dave.
Thank you, Dave.
Bye.
Thank you, everybody, for attending. So bye-bye.
Bye-bye.